Hello, good evening everyone, welcome back to the second video in my series on linear algebra number 1. I just want to preface this video by saying that I believe I am no expert on this topic, and I believe that everything I'm saying is indeed correct, but if I do make any mistakes I deeply apologise, and please do correct me kindly in the comments. That being said, let's get straight back into this. So last time we looked at linear systems, and I guess specifically everything that we spoke about last time is right here. So we defined the linear system, and then we spoke about what it means to be a solution of that linear system, and in particular, I guess, what it means for a system to be consistent, and what a general solution is, and also what an augmented matrix is. We follow that up by looking at an example with substitution, then defining EROs and some notation, and finally sort of going through the process of row reduction, which is really our sort of updated substitution method, which is a lot easier to program in general. So so we spoke about row reduction, we sort of compared the substitution, and we looked at some examples. And today I want to look at some other examples where things aren't so easy. In the example we looked at last time, there was a very clear, unique solution, and hence we had that sort of identity matrix, or that 1, 0, 0, 0, 1, 0, 0, 0, 1 matrix at the end there. But this time we are not going to get that sort of output even after we reduce the augmented matrix, and we need to be able to know when our linear system has 0 solutions or when it has infinitely many solutions. So let's have a look at some more examples today. Okay. So let's have a look at some examples. So, example. So I'm going to look at two examples. The first one, and both of the examples are asked to find the general solution. The general solution to the following linear systems. Just see how this is on my computer. Okay, that's fine. So the following linear systems so I guess the first example, right, let's spell following correctly. Okay, nice. First example I want to look at goes a little bit like this. So we have x1 minus x2 plus x3 plus 3x4 equals 2. So that's our first equation. Our second equation is 2x1 minus x2 plus x3 plus 2x4 equals 4. And our third and final equation is 4x1 minus 3x2 plus 3x3, add 8x4 equals 8. Okay, so last time we went through sort of how we would sort of use row reduction to sort of reduce a system like this into a form where we can just read off the solutions. And even though in this case the sort of end product will be slightly different to the end product we saw last time, the first stage is still very much the same. We should still start by converting this into an augmented matrix. So we can sort of convert the system into an augmented matrix as follows. So you always just get rid of these x1s, get rid of these x2s, get rid of these x3s, get rid of these x4s, and you place 1s in front of or minus 1s, depending on whether there's a minus or a plus in front of the variables which don't have any coefficients in front. and then you just basically take each of those coefficients and you place it in a matrix with a line, and then you place the 2, 4, 8 on the other side of that line, because the line acts almost like an equals. So we have our augmented matrix. So I guess to just condense that into one visual, we can just draw out the augmented matrix as follows. So it's going to be 1, 2, 4, minus 1, minus 1, minus 3, 1, 1, 3, and 3, 2, 8, followed by a line, and then 2, 4, 8. So this is our augmented matrix here. So this is always the first thing you should do when using row reduction, is to just convert your system into an augmented matrix, just really abstract the names of the variables which don't really matter. And now we can use our EROs on that augmented matrix and try to reduce it. Remember, whenever we're trying to reduce it, our aim really is to have sort of, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, right? And then like a bunch of stuff, A, B, C, D, something like that, right? We're looking for this sort of identity matrix on the left-hand side. Now, it should be, immediately clear to you that we can't quite get that, right? Because we need 4 rows to do that. But nonetheless, we're going to try our best to get something that looks somewhat similar to that, just missing a row. So let's see what happens. So I'm going to sort of, instead of going through each ERO individually, I'm just going to tell you sort of pairs of EROs, and then you can do sort of the calculations yourself. But first of all, we're going to add minus 2 times row 1 to row 2, and follow that up by adding minus 4 times row 1 to row 3. Okay, and this gives us the following matrix, following version of our augmented matrix. So we have 1, 0, 0, minus 1, 1, 1, and then 1, minus 1, minus 1, 3, minus 4, minus 4, in the line, and 2, 0, 0. Okay, so you can see we already have this 1, 0, 0 here. Now obviously we can't get the exact identity matrix that we want over down here, but we do indeed have a 1, 0, 0 there, which is reminiscent of an identity matrix. And then we can follow this up by doing applying some more EROs. So we're just going to add 1 times row 2 to row 3, and then add minus, sorry, I meant row 1. Add 1 times row 2 to row 1, and then add minus 1 times row 2 to row 3. And that will give us the following matrix. That should give us 1, 0, 0, 0, 1, 0, 0, minus 1, 0, minus 1, minus 4, 0, followed by a line here, and then 2, 0, 0. So we do indeed have this sort of identity-like structure here, 1, 0, 0, 0, 1, 0. So that kind of catches your eye. But there's also another thing that we have here, which is a third row of just zeros. Now, what does this really mean? So let's have a think about that. I'll just have a think, and I'll talk through some other things before we properly discuss. So obviously, this is still representing the same system, since whenever you apply EROs, it's not going to change the information in that system. The information is still there. So this is representing, this augmented matrix here represents the same information as the augmented matrix we started off with. And so basically our initial system is now basically reduced to the following system. So we have 1 lots of x1 plus 0 lots of x2 plus 0 lots of x3 and plus minus 1 lots of x4, and that has to be equal to 2. So another way we can say this is just that x1 minus x4 is equal to 2. So that's the first sort of row there. And our second row tells us that x2 minus x3 minus 4x4 has to be equal to 0. So those are our first 2 rows. And then our third row just tells us basically that 0 x1 plus 0 x2 plus 0 x3 plus 0 x4 equals 0. which is true no matter what x1, x2, x3, and x4 are equal to, right? So effectively, that isn't really telling us anything other than 0 equals 0. Well, thank you, but I think we all know 0 is equal to 0. So we can kind of just get rid of that, and then effectively our system is just described by these two rows here, the first two rows. Can we solve this though? Is looking a bit sort of this should be 4x4 here, by the way. Don't know why I put 4x3. But it's looking a bit bleak, if I'm being honest with you, because we have 4 variables but only 2 equations. It was looking a bit bleak from the start, to be honest, because we could never really get this 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 because we just didn't have enough rows. So there was already a problem there. But now that we have even less rows, it's very clear that there's not going to be a way to find some unique solution here. What does that really mean for the solutions? Well, I think it's first important to note that whenever you see zeros like this, it's an indicator of redundancy. So it means that one of the equations that we started off with was actually just one of the other equations we started off with, but changed somehow. And actually what happened here, if we go back to the initial system we started off with, then effectively the third equation here can actually just be derived from the first two. So the third equation was 4x1 minus 3x2 plus 3x3 plus 8x4 equals 8. And we can derive this from the first two equations by effectively multiplying the first one by 2. So you do 2 times x1 minus x2 plus x3 plus 3x4, and then adding the second equation to it. So adding 2x1 minus x2 plus x3 plus 2x4. So if I do this, this will be my left-hand side. What I'm going to notice is that I'm going to get, well, you can already see here, 2x1 plus 2x1 is 4x1 minus 2x2 minus x2 is minus 3x2, 2x3 plus x3 is 3x3, and 6x4 plus 2x4 is 8x4. So this just gives me what my third equation, right? So my third equation is actually just 2 times the first equation plus the second equation. So it isn't really any different. It's just the same as the first two, right? I haven't introduced any new condition. I've just used the conditions I have and applied some EROs to them, which gives me effectively no new information, right? That's what EROs, that's one of the properties of EROs, is that they don't change the information in the system. So I've added in a third equation which secretly has no new information in it, which means that in reality I only really had 2 equations to start off with. So clearly there's some redundancy there, and that's what the zeros. That's why row reduction. The reason row reduction is really nice, because it gives us these zeros, these characteristic zeros, which tell us that clearly one of these equations was a bit sneaky and is actually redundant. So that is a nice sort of thing that comes along with row reduction, and can be particularly tricky to spot with substitution. So is better, and this is why one of the reasons, and again, why row reduction could be considered better. And yeah, I guess, and then yeah, you just see that just gives you 8, and that is just our third equation, right? So redundancy, so redundant system. So well, I'll just say there's some redundancy, and then some exclamation marks because no one likes redundancy. Okay. Right. So we understand there's some redundancy here. And as I've said, we only now have 2 equations in 4 variables, right? So if we go back to what we had over here, well, it's very clear that with the x1 minus x4 equals x2, x2 minus x3 minus 4x4 equals 0, it's very clear we have 2 equations but 4 variables, and so it's impossible for us to get the identity-like structure, and it's just impossible. There is no way to do it, right? Simply not enough rows in our augmented matrix to allow that to happen. Because effectively, now that we have this row of zeros, it's like taking another row away, so it's made it worse. So we already had 3 rows, which was looking bleak, but we took one away, so it's made it even worse. So yeah, basically this is not going to be not going to be any unique solution. And so now, how do we actually find the solutions to this? Well, are there any solutions? Well, the answer is yes, and there's actually infinitely many solutions to this system, because there's no possible way for us to solve for each of these variables independently. There's also no way for us to say that, you know, this system is, you know, not possible, right? Like, there's nothing indicating that it's not possible, and so we are going to effectively we're effectively this means that there's going to be infinitely many solutions, and we can just effectively describe these solutions, and because we can describe them, it also shows us that there must be infinitely many. So let's think about how we describe these solutions. Okay. Well, one thing that we do typically when we're at this point in time, and we have the augmented matrix that we want. So in this case, it was 1 0 0 0 1 0, and then we follow that up with 0 minus 1 0 and minus 1 minus 4 0. And then we just had that sort of line there, and then 2 0 0. So one thing that we typically do is we look at our columns, and they're going to give us some nice insights. So I look at my first column, and I'm going to look for leading entries. And what a leading entry is just basically just the first non-zero entry in a row. So if I look at each of my rows, the leading entry of my first row will be 1. The leading entry in the second row will be again 1. And there's no leading entry in the third row. So I look at my columns, and if my column contains a leading entry, then I'm like, nice, that's good, and I take it off. So I look at my first column, it contains the leading entry here, so that's nice. I look at my second column, it contains the leading entry here, that's nice. I look at my third column, this doesn't contain a leading entry because minus 1 is not the first element in the row, in its row, and so what that means is I need to effectively assign a parameter to the variable corresponding to this column. There's a good reason for this, and it's because, well, it's really because it's a free variable, which means that it can take any value we want. There's no restriction on what x3 really could be. Same is true here with x4. So effectively, x3 and x4, these are free variables, and the reason the reason we know this is because, as I said, we look in the column, we look for leading entries, and notice that there aren't any in the third and fourth row, and so hence this tells us that x3 and x4 are free variables. And so what we now do is we assign parameters to them. So we say x3, we're going to call that s, right, where s is just some real number, and x4 is going to be equal to t. And what I can now do is I can effectively describe the remaining solutions of my system in terms of those two parameters that I've introduced. So very clearly we have from before, in my earlier box, we have that x1 minus x4 is equal to 2, but x4 is just t, so I have x1 minus t is equal to 2. So x1 is actually just equal to t plus 2. And so what I've done here is I've taken a free variable and I've expressed my other variable, which isn't free, in terms of that free variable, right? And so effectively this is what us looking at the columns and identifying the leading entries is doing. it's identifying which variables we can express everything else in terms of, and then we parameterize those variables, which means we assign parameters to them. Okay, and also notice that we had from before x1, what was it? Sorry, x2 minus x3 minus 4x4 is equal to 0. So this therefore gives us, and we know x3 and x4, they're just s and t, so we can just say s, and we can also just say t, so this gives us x2 is equal to s plus 4t. And so we've now expressed x2 in terms of both s and t. And so what we say here is that our most general solution, so our most general solution, so we have that our most general solution is, in this case, just going to be the vector x1, x2, x3, x4, which is equal to t plus 2, s plus 4t, s, and t. And we can actually also write this in another format if we want to, which is as follows. So we have 2, 0, 0, 0 plus s times 0, 1, 1, 0, and then plus t times 1, 4, 0, 1. So you can basically treat these as row vectors if you're familiar with those. Sorry, I should move this down. You can treat these as row vectors if you're familiar with those. And so effectively what you get is you just add up each of these components. So you do 2 plus s times 0 plus t times 1, which is just t plus 2. And then you can look at the second component, which is 0 plus s times 1 plus t times 4. So that gives me s plus 4t, which is indeed corresponding to my x2. So this is just the same way as writing this, but just slightly different. And you might sometimes write it that way. The reason you might sometimes write it that way is because it tells you something about what geometrically the solution of this linear system is representing. Specifically, and I won't go into too much detail on this, it actually represents a plane in R4, which is a four-dimensional coordinate space. So if you've ever seen the parametric equation of a plane, then you will know that this is a plane passing through the point 2, 0, 0, 0, parallel to both 0, 1, 1, 0 and 1, 4, 0, 1, with st parameterizing the plane. But again, that is slightly unimportant, but quite an interesting sort of result, that actually the solutions to these linear systems can be thought of geometrically, and that connects some fields of maths there. So I guess do have a little look into that if you're unsure about parametric equation of a plane. It does show up in the geometry course as well, so maybe I'll make a couple videos on that. But for now, it's just a nice, interesting consequence to have a think about. Okay, nice. So let's have a look at our second example. So we looked at an example with infinitely many solutions. So we looked at an example with infinite solutions, in which case we have our characteristic zeros. And we also have, we also used parameterization to describe our general solution. Right? So those are the two main things you should get from the infinite solution case that extend from typical row reduction. Okay, very nice. So let's have a look at our second example here. So for the second example, I want to have a look at the following system. So we have x1 plus x2 plus x3 plus x4 equals 4. And we also have 2x1 plus 3x2 minus 2x3. minus 3x4 equals 1. And I'll finish off, let me just make sure this is also visible, by saying, again, we only have 3 rows here, x1 plus, I'm going to have 0 here, plus 5x3 plus 6x4 is equal to 1. So, well, it's already a bit concerning because we have 3 rows, but let's see what happens here. So again, you want to convert this into an augmented matrix, so we put 1s in front of the sort of variables that don't have any coefficients. So then we just put 1 in there, we strike out all of these variables, it's technically an x2 in here, strike out these variables, put 1 in front of that, put 1 in front of the x4, strike out those variables, and we place them in our augmented matrix. So yeah, we just do 1, 2, 1, should put 1 here, 1, 3, 0, 1, minus 2, 5, and 1, minus 3, 6, followed by a line, and then 4, 1, 1. And so we start doing our augmented matrix stuff. Of course, we aim to get some, identity matrix stuff going on, and so we do a bunch of sort of, we apply some EROs to it. So we're going to add minus 2 times row 1 to row 2, follow that up by adding minus 1 times row 1 to row 3, and this gives you the following augmented matrix: 1, 0, 0, 1, 1, minus 1, 1, minus 4, 4, 1, minus 5, 5, and then 4, minus 7, minus 3. And then we'll follow this up by adding adding 1 times row 2 to row 3, and so this will then give us the following augmented matrix. So it's just as 1, 0, 0, 1, 1, 0, so 1, 0, 0, 1, 1, 0, 1, minus 4, 0, and then 1, minus 5, 0, followed by 4, minus 7, minus 10. You might already see something wrong with that, but we're going to keep going, and I'm going to just keep applying some EROs to this. Well, I'm going to multiply row 2 by minus a tenth, and then I'm going to follow that up by adding minus 1 times row 2 to row 1. Sorry, I meant row 1, and that gives me the following augmented matrix. So 1, 0, 0, 0, 1, 0, so that's looking nice. Minus 4, minus 5, minus 4, 0, minus 6, minus 5, 0. So we're kind of losing the plot here a bit, but then we also get minus 11, minus 7, 1. So here's the problem. Clearly, this third row for us is a big problem, because if you just have a think about what that's telling us, well, it's telling us that any solution of this system, right, since we haven't lost any information by applying EROs, so any solution to this linear system, must also satisfy, so it must satisfy the following equation: 0x1 plus 0x2 plus 0x3 plus 0x4 equals 1, which is clearly telling us that 0 is equal to 1. So that's obviously not true, hopefully. And so clearly there are no sort of values x1, x2, x3, x4 which would ever solve the system, because no matter what I let them be, that third row will always be false. And so our system has no solutions. So our system has no solutions. And that can also happen, right? And there's that example. And you could also see this, I guess, in the sort of second to last augmented matrix. We have 0, 0, 0, 0, and then a minus 10. That's clearly telling us that 0 is equal to minus 10, which is also wrong. But there is a reason as to why we did a little bit more to it, which will become clear when we look at reduced row echelon form later on in the course. But for now, just know there was a reason we did that, and have a think about why that might be. Okay, so also I think it's worth noting that now that we've looked at these examples, the following statement is true. A linear system can have no one or infinitely many solutions. And I should also actually note how we know there's going to be zero solutions. So whenever we do row reduction, we can also tell there's going to be zero solutions because of this row at the bottom here. That's specifically what tells us there's going to be zero solutions, because of the fact that 0 cannot equal 1. So whenever there's zero solutions, you just look for contradictory row. Contradictory row after applying EROs. So that will give us something like 0 equals 1, right? So that's, I guess I should put e.g. 0 equals 1. That's a contradiction. And we might see that in one of our rows, which means it's going to be 0 solutions. Okay. So there we go with that. And there's that statement that a linear system can have no one or infinitely many solutions, that we should be thinking about why that's true. And we can prove that later, but for now, let's have a look at a linear system involving a parameter to finish off. Now, really, a linear system involving a parameter is actually basically just like a family of linear systems all in one. Because for any value of that parameter that I pick, I get a different linear system, which means that actually, if I just have a sort of family of linear systems, some of them could have 0 solutions, some of them could have 1 solution, and some of them could have infinitely many solutions, depending on the value of my parameter. And so that means that actually this will be quite interesting, this example, because even though it looks like one linear system, my parameter gives me all possibilities as I change its value. So that will be interesting. So let's have a look at this final example to end up the chapter here. So example. Okay, so consider the system. So consider the system of equations. So I'll turn on my fan for a second. So the system of equations in x, y, z. That look like the following. So the first equation we have is that x plus z equals -5. So that's number 1. Let me just check this is still on my screen. Yeah, perfect. The second equation that we have is that 2x add alpha y plus 3z, sorry, give me a second here, plus 3z is equal to -9. So that's our second equation. Then our third and final equation would be that -x minus alpha y, and then we had plus alpha z is going to be equal to alpha squared. So that's our third equation here. Right, and we have alpha being, I guess, a real constant. Alpha is a real constant. Okay, I guess the question that we want to answer is, for which alpha does the system have 0 solutions, 1 solution, or infinitely many solutions? So that's the golden question here. As I change my value of alpha, how does that affect my solution, my sort of set of solutions? So let's have a look at this. So the first thing that we always do with these systems is well, when we're doing row reduction, is we immediately abstract them into an augmented matrix. So we do that here, and our augmented matrix in this case will be 1, 2, minus 1, 1, alpha, minus alpha, and 1, 3, alpha. And also on the right-hand side of that equals, we have minus 5, minus 9, and alpha squared. Okay? And in this case, it's absolutely fine that we have alpha here, right? Obviously, we don't have the names of our variables x, y, and z in there, but alpha is not a variable, it's just a constant, right? It's fixed in each specific case, but it varies over all possible cases to give us a family of linear systems. Okay? So I guess then what we'd start doing is trying to get this into our typical form, right? We want to get this into the identity matrix form, and there's nothing inherently here that says that that's not possible at the moment, because there is 3 rows here, so we can indeed get 1, 0, 0, 0, 1, 0, 0, 0, 1, and then some ABC on the right hand side. So it does seem possible. So let's see what happens. So we're going to apply some EROs here. So the first thing we're going to do is add minus 2 times row 1 to row 2, and then add 1 times row 1 to row 3. And this gives us the following augmented matrix. So we get 1, 0, 0, 0, alpha, minus alpha, and then 1, 1, alpha plus 1. And then sort of this line here, which is representing the equals, then minus 5, 1, and alpha squared minus 5. And then we can add 1 times row 2 to row 3 to give us the following system. 1, 0, 0, 0, alpha 0, and then 1, 1, alpha plus 2, and then minus 5, 1, alpha squared, minus 4. Okay, so let's think about what we can do here. So we already have this 1, 0, 0, so that's looking pretty nice. We want to have a 0, 1, 0 in here. So what that's going to involve is me dividing somehow by alpha. If I divide by alpha, then I'm going to be worried if alpha is equal to 0. Because we haven't said that isn't possible. So if we're dividing by 0, that's going to give me a problem. So that's something to notice. But we also eventually are going to want to have a 1 in this position here with the alpha plus 2. So that might entail me trying to divide by alpha plus 2 as well, which means that alpha cannot be equal to minus 2. So we need to be worried about those 2 cases. And so what we're going to do is we're going to now assume that those 2 things aren't true. So we're going to assume that alpha is not equal to 0, and we also are going to assume that alpha is not equal to minus 2, so that alpha plus 2 is not equal to 0. Okay, and so this means that we can now do the following to the linear system. So we had 1, 0, 0, 0, alpha 0, and then 1, 1, alpha plus 2, and then minus 5, 1, alpha squared minus 4, we can now basically multiply the second row by 1 over alpha, and then multiply the third row by 1 over alpha plus 2, right? And so what this is going to give us is a new system, so we're going to get 1, 0, 0, 0, 1, 0, 1, 1 divided by alpha, and then 1. And then we also have our line here. And then after that line, we're going to have the following values: minus 5, 1 divided by alpha, and alpha minus 2. And we can finish this up by now all of a sudden doing a couple of things to this. So we can add minus 1 times row 3 to row 1, and then we can multiply, we can add minus 1 over alpha times row 3 to row 2. And this gives us our final augmented matrix: 1, 0, 0, 0, 1, 0, 0, 0, 1, and on the right hand side we have some values in terms of alpha. So minus alpha minus 3, 3 divided by alpha minus 1, and then alpha minus 2. Okay, and so we can see here that we have a unique solution, right? So it's very clear that if we just assume alpha not to be 0, and alpha is not also, we also assume alpha not to be minus 2, then we just get this lovely identity matrix format here, which gives us our unique solution, as we would have hoped. But what happens when alpha is equal to 0, and what happens when alpha is equal to 2? So we need to really think about what's going to happen in those two cases. So if I just go down, so what happens when, first of all, alpha equals 0? So in this case, we just go back to the part we were at before we divided by 0, and we just let alpha be 0. So this just gives us the following matrix. So we just have 1, 0, 0, 0, 0, 0, and then 1, 1, 2, and then a line, and then minus 5, 1, minus 4. And we can apply some EROs to that. So we can basically multiply, so we can add minus 2 times row 2 to row 3, and multiply row 3 by minus a sixth. And this therefore gives us the following matrix: 1, 0, 0, 0, 0, 0, 1, 1, 0, and then a line, and then minus 5, 1, 1, at which point we can stop, because we see this sort of row here, this contradictory row. So contradictory row is an immediate sign to us that we have 0 solutions. So contradictory row, 0 solutions. So when alpha is equal to 0, we do not have a unique solution. In fact, we have 0 solutions. Okay. So for that one particular value, that gives us 0 solutions. For all other values, it either is minus 2 or it has a unique solution. So what happens when alpha is equal to minus 2? Well, in that case, alpha is equal to minus 2. You might be able to guess, but we can just plug in our sort of alpha equaling minus 2. That gives us 1, 0, 0, 0, minus 2, 0, 1, 1, 0, and then minus 5, 1, 0. So immediately we see this characteristic row of zeros, which is a big sign. That, in fact, that is pretty much the sign that tells us that this will have infinitely many solutions. But again, we just continue to try and get this into our identity matrix form. So we multiply row 2 by minus a half, and this gives us 1, 0, 0, 0, 1, 0, which looks promising, but then we get the following: 1 minus a half, 0. And it's really that third 0 that is sort of the nail in the coffin here as to how many solutions we're going to have. And so you can immediately see here that we again have this characteristic row of zeros. And in this case, we can assign, we can look for our sort of leading entries. So in this column, leading entry is here. In this column, leading entry is here, but there's no leading entry in here. So in this case, we'll just say that Z is equal to, let's say, T. And then in the second row, we see that Y minus half Z is equal to minus a half, but Z is equal to T. So we can just replace that, and we get that Y is equal to sort of a half, so minus a half plus a half T, which is the same thing as, I guess, T minus 1 all over 2. So we've then written Y in terms of Z, and which is just T, and we can also now write our X in terms of Z, because in our first row we have that X plus Z is equal to minus 5. So we have that X is equal to minus 5 minus T. And therefore we have now sort of used parameterization to basically describe our most general solution, which would be, in this case, X, Y, Z. So this case is infinitely many solutions. And our general solution is described by the vector row vector x, y, z, which we can write as minus 5 minus t, t minus 1 over 2, and t, like so. And that's when alpha is equal to minus 2. Okay, and with that, we are done. That brings us to the end of the second part of this video series on linear algebra, and that is the end of our discussion for now on linear systems. So thank you very much for joining me, and do ask any questions, make any corrections in the comments, But for now, I'll see you guys later. Goodbye.